Welcome everyone. In the last few episodes, we discussed what is an involution and we defined involution on line, points on a line, and points on a circle, and pencil of lines that are concurrent at a particular point. For example, involution is just a function that when taken twice gives back the same point, and it preserves the cross ratio when that function is applied. Like if you take x, y, z and w points, the cross ratio of them will be equal to the cross ratio of the points obtained after applying that function. So the function takes a particular configuration to the same configuration. So it has to ensure just these two conditions. So please have a look into the earlier episodes if you want a great detail of these discussed. Now in this discourse, we will take a look into Desargues' involution theorem, which is one of the ultimate goals of our involution series. Let's get started with the statement. The involution theorem goes by the word Desargues, and the idea behind this uses one of the properties of involution we derived earlier. We derived that two involution pairs define an unique involution. We are going to use that. And moreover, cross ratios are preserved upon this involution, and the cross ratios are preserved even upon projections. This is a part of projective geometry which also we dealt with. The statement goes this way. Suppose I consider a circle as shown and a cyclic quadrilateral ABCD in it. The diagonals are drawn, AC and BD. We construct a random line on the plane to intersect AB at x1, CD at x2, and the two opposite sides AD and BC at y1 and y2 respectively. Circle at w1 and w2, the diagonals at z1 and z2. So z1 lies on AC and z2 lies on BD. The names or the indices 1 and 2 do not actually matter, because the final statement is that the pairs x1, x2, y1, y2, w1, w2, z1, z2 forms an involution pair. Well, we saw that any two involution pair defines a unique involution. That means if I consider these two pairs, w's and xi's, then it turns out the other two pairs also follow the same involution map defined by them. This is what it means. The next, we are going to prove this theorem. But first, we have to understand what this actually means in the ideas we derived. This means there exists a function or involution function f such that it maps w1 to w2, y1 to y2, and the reverse, w2 to w1, y2 to y1, x1 to x2, x2 to x1, z1 to z2, z2 to z1. And this map preserves the cross ratio. We know that any map that preserves cross ratio and is an involution is nothing but an inversion map. Inversion about a point on the line, for some radius of inversion. Alright, let's prove this theorem. Supposing we consider the cross ratio x1, y1 to w1, w2. I'm going to prove that it leads to x2, y2 is to w2, w1. Then, by assuming the function f to be defined by the pair w's and xi's, I know that y1 is taken to y2. Similarly, I can work with z1 instead of y1 to have that z1 goes to z2. So like, I'm using the inherent property of involution here. Mind you, two involution pairs define an unique involution for any configuration, be it the points on a line, be it points on a circle, or concurrent lines, or famously known as pencil of lines. So let's project it about the point A. So when you project x1, y1, w1, w2 are collinear points. They are now mapped to concyclic points. x1 goes to B, y1 goes to D, D for Delhi, and w1 stays at w1. We are projecting to circle. Now we have BD and w1, w2. So I am going to project the points on the circle back onto the line. B should come to y2, like that's what it seems to be, right? Another point lying on the line joining two vertices. So let's project from C. B goes to y2. You could see that B goes to y2 when I project from C, and D goes to x2 when I project from C, as DC, x2 are collinear, whereas w1 and w2 stays the same. So by the properties of cross ratio, I can rewrite that as x2, y2 is to w2, w1. Well, effectively, x2 is f of x1 by our assumption. So remember that the first two wi's and xi's are the one defining f. So f of x1, you have y2, and w2 is f of w1, and w1 is f of w2. Therefore, we get here that f of y1 should be y2. That's what the function takes to. So we get that y1, y2 forms an involution pair. Similarly, a y2 will be taken back to y1 because involution function when applied twice should come back to the same element. Okay, how about z1 and z2? Similarly, if you work with x1, z1 is to w1, w2 with a different point of projection. So you have x1 and z1. For now, for the first step, we will assume A as the projection. As earlier, x1 goes to B, whereas z1 goes to C. You could see that when projected from A, z1 maps to C. So it goes to C, and then you have w1 and w2. Now let's take the point of projection to be D, because you have to turn B and C into some other points on the line. So if you project it from D, B maps to Z2, C maps to X2, W1 and W2 remains the same. Writing it equivalently, I get X2, Z2 is to W2, W1, and this is f of x1, Z2 is to f of W1, f of W2. So notice that f of Z1 equals Z2. Therefore, we conclude that by assuming xi's and wi's, y1, y2 and z1, z2 form an involution pair. This is the Desargues involution theorem. And in the upcoming video, we will see the dual of this. So stay tuned. Thank you. Bye.